All right, thanks, and hello everyone here and all the rest on Zoom online. I hope you can still hear me. I guess so, so that's perfect. As Olivier just said, so maybe I can also say something about me first, so who I am. So I'm usually a physicist, but I'm a machine learning scientist as well by training, I would sort of say it like that. So I use a lot of machine learning, or especially neural networks, and as an application within high energy physics. Today I won't do that, so I really start with basics of neural networks and give you some ideas, some intuition about it. So let's have a first look of our plan of attack for today. So I first want to talk a little bit about some basics and intuition about artificial neural networks. Then we do some code example where I directly go through some basic TensorFlow code, and then we actually elaborate some business problem I'm going to talk about. Then I will shortly also introduce you into convolutional neural networks, because they're really, really important in almost all contexts where you have images involved. So this is pretty much important for almost all scientific areas, I would say. And then in the end, there will be, again, some code example where there would be a task for you to actually hands-on write your own machine learning code to distinguish cats against dogs. So it's going to be interesting, and I think this should work. So let me shortly say something about all the material. So if you go on the website of the CC cluster, where today's session is online, there are essentially all material online. So here's the PDF of my talk. If you want to go through it later or something, you can find everything there. And I also already uploaded the notebooks, which we need later for the Python session part. I don't gonna go into too much details now, because I'm gonna explain it to you later when we actually need it. But there will everything you need to find. Okay. Perfect. So the first thing I want to talk about is artificial neural networks. And yeah, one other thing I want to shortly mention is we have in principle 3 hours today. So after 4:15, I think it makes sense, especially because it's kind of split up into hands-on parts and also a little bit like more this, let's say presentation type, that we split in the middle or something, or if you prefer, we can also split in, I don't know, twice after every hour, doing some 5 or 10 minutes break. We can just see which fits better. So yeah, can go to toilet or drink something. All right, so let me start with artificial neural networks. If you want to talk about artificial neural networks, whatever comes into your mind, and this is what's also mentioned on this word cloud, is you also think about machine learning. And the first thing you really have to define and talk about before you can really talk about neural networks is, what is machine learning? And I found this nice sentence, I think it was on Wikipedia, I guess, which defines machine learning in one little really short sentence, which is: machine learning is the study of computer algorithms that improve automatically through experience. Okay, what does it mean? So you have different parts in here which are important. First of all, you have the algorithm, which is the method you use to perform a task of interest, which in our case will then be the neural network. Second, you have some experience, which is in most cases the training data you learn on. Then obviously you want to improve over time, so you need some kind of quality measure in order to know if your method improves or did not improve. That's something which is the loss function, and we also talk about that. And last but not least is you want to have it automatically, which means you need some kind of strategy in order to exploit the data without doing any kind of external input or anything, which is linked to the idea of training. And these are essentially the 4 main ingredients you need for doing machine learning in general. The thing we are interested in today, or what I would like to focus on, is about a specific algorithm, which are neural networks. But of course, there are way more other algorithms out there, and machine learning is not just neural networks. Every neural network is machine learning, but not all machine learning methods are neural networks. Okay, so what are neural networks? There, in principle, you can also define it first in order, and then you can like more disensemble different parts. So a neural network is just, if you define it plainly, some interconnected assembly of simple processing elements, units or nodes, whose functionality is loosely based on the human neuron. And this human neuron I try to sketch down here. And then you also call the process of ability of the network is stored in the inter-unit connection strengths, or we call them weights. And they are obtained by a process of learning. Okay, this is a long sentence and not all of it is particular interest. So I kind of help you with that. What is important? So there are essentially, let's say, 3 or 2 important parts of the neural network. This is the unit part on the number of nodes you have, and the weights, because the weights is essentially the main building block you need in order to get some differences, because that's what you adjust, that's what you vary. And this is obtained by learning. Okay. Okay. Let's look into this a little bit, not that much from the biology science, but more from the mathematical and also scientific science. So every neural network consists of a huge number of artificial neurons. And these are essentially the main ingredients of artificial neurons. So first of all, you have some neuron, which is like that one. And you have some inputs to this neuron. And these neurons or these inputs are summed up, but not just normally, they're summed by their weights. They're summed, so you have a weighted sum with those weights W here. On top of that, you can also add some bias, which you just add to everything. But in principle, your ability to learn things with a neural network is not limited or not restricted to cases where you have this bias. So this bias can also be 0, but this is just an additional parameter you can learn. And one crucial thing, people most of the time forget when you talk about neural networks. So most of the time when people talk about neural networks, they really just think about these weights, and if you have to sum up, and then you feed forward this to the next neuron, etc., and you sum everything up. But this alone doesn't help you, because if you think of that, what if you would do this without this activation function? I will talk about this in a minute. The only thing you get would be essentially a linear map, because you're just multiplying weights with some input, and even if you add multiple neurons, it's essentially just multiplying several numbers of linear matrices. So you can definitely describe some mappings, but only linear ones. This is okay if you're only interested in a linear problem, but the big application, or there where you really want to use neural networks for, is in nonlinear problems. So we definitely need something which brings nonlinearity into your construction. And this is where this activation function comes in here. And this is applied on top. So obviously this activation function, in order to bring in some nonlinearity, needs to be some nonlinear function. So if this is just f of x equals x, then you don't gain anything. So you need something nonlinearity. There are several different kinds of linear activation functions used in the literature. I will show some of you in a couple of minutes. And they have different features and just different advantages and disadvantages. You will see in a second. Okay, so how do we get now from this one neuron to a proper neural network? So obviously one neuron alone, well, it describes something, but you definitely want a more powerful description. So what you usually do, obviously, is you not just use one neuron, you use several of them, which you connect. For instance, here, this is like a really simple, it's a neural network, but it's still a really simple one, where you have one input, then you have, let's say, 2 or 3 layers with Each layer has here 3 neurons, 2 neurons and 1 neuron. And then you see the output in the end is essentially just this combination of the different functions you can have. So you can pass this input through all the different nodes and sum everything up, weighted with the weights and combined with the whatever activation function are used in this specific neuron. And you can see if you use a lot of layers, this can become really, really complex and not really easy to track. So because in general, in most cases, you're not using this shallow network with like 2 layers here and just 3 neurons. You rather use like really, really deep neural networks. Like here, I just call the number of hidden layers n. But in principle, you're not restricted to some numbers. You can just say, okay, I go with 100 layers, and each layer consists of, I don't know, 100 neurons. And then you can think of, if you stack all of that, you get a lot of combinations and a lot of parameters you can adjust. And then this whole output becomes really, really complex. And obviously highly nonlinear, which is also what you want, because you want to use, in principle, neural networks for nonlinear problems. Okay, something which is important about this picture here is that even though in principle a layer is not really different from every other layers, you usually classify them in 3 different kinds of layers. So you usually have something like an input layer, which is, let's say, the first layer you really put in your data which you're training on. And that's the layer you have access to. Then you have a bunch of hidden layers where you do not really know what's going on. I mean, of course, if you want, you can always look into different values, but you're not really interested in what's going in those hidden layers. That's kind of sometimes what people refer to as a black box for machine learning. And in the end, you have an output layer. And the number of output nodes depends on your problem, on the dimensionality, and also on what you're interested in. So for instance, if you would like to fit a one-dimensional function and your output then is obviously just this function value, you would only have 1 neuron in output. If you have a multi-dimensional function, you would have as many neurons as you have dimensions, for instance. So the number of output really depends. And also the value of your output also depends on what you're interested in. If you're doing a regression, really the output value should be your function value, or let's say a scaled version of that. What I mean by scaled is that in some cases it can be beneficial if you pre-process your data before you feed it into a network. I will talk about that later when we actually work on an example. Okay, but this is essentially what you really need for neural networks. So you need your neurons, which are connected with each other with weights. You need your activation function, which is nonlinear, and then you stack everything, and then you can put in your whatever information is. So for instance, if you think of a regression, you put in your x values in no matter how many dimensions, and you want to fit, for instance, a function, and this is your output. Okay, what are typical kind of activation functions people use? So as I said, let's say if you're only interested in a linear problem, you could really well just go ahead and just use a linear function, because if you know your problem is linear, there's no need in principle to use a nonlinear function. But obviously, usually when you set up a neural network, you usually encounter problems where you don't know a priori what you're expecting it looks like, right? So you better don't do that. But there's actually kind of a twist, because people realize that you do not really have to do that much in order to get something nonlinear out of a linear function. And this is what you can see on the right. This is the so-called rectified linear unit. And what you do here is essentially you keep the linearity for positive input values, and for everything negative, it's just 0. So you essentially throw it away. This is pretty nice because it's really, really simple. Because the two things you need, and you will see this also a couple of slides, is you need to evaluate the function itself, which is obviously easy in a as a linear function, because it just returns the value itself if it's positive, or it's 0 if it's not. And the other thing you need later for the training is the gradient. So in this specific case, the gradient is also pretty easy because it's just a constant. It's 0 for everything equals to 0 and below 0. And it's 1 if it's positive. So that's a fairly easy one. Then depending on the problem, you can also use different kind of activation functions, because people realized that this ReLU function actually sometimes has issues. So for instance, people realized that in some cases it's not smart if you throw away all the zeros, all the negative numbers, because what can happen is that if you have a big stack of neurons, so meaning a deep neural network, is that over time the gradients you have to calculate vanish, because you're essentially throwing away a lot of numbers, because it's quite likely that numbers getting 0 are below 0. So a way around it is this so-called leaky ReLU function, where you essentially still have an activation for the negative part, and this is here highly exaggerated, but you just use a really less steep linear function for the negative part. What you usually use, or is like the standard thing, is something like 0.1x, for instance. Another thing which might be problematic in some cases is this, let's say, non-differentiable value at 0, because here you have this problem that it jumps. So you can like more use a smoother transition, which is this ELU, which is like more, smooth in a sense, and this can also help sometimes. And also this depends on the problem, of course. But all of these three functions, I would say, they are rather new. Originally, people were rather thinking about this upper left one, which is the sigmoid or logistic function. And the reason for this is because when people were thinking about neural networks in the beginning, they were also always thinking and associating that with how does a neuron works in the human brain. And there, you know, at least you might know that you usually have some thresholds. So whenever you reach some certain value, it passes through, and then you get some damp activation, which is also limited. So no matter how much input you put into your neuron, there's just this maximum amount of electric impulse your neuron puts forward. And this is kind of linked to the sigmoid, where if you have small values, you have a small output, which goes to 0 if nothing comes in, essentially. And then it increases to some big value in the end. The nice thing about the sigmoid is, even though it looks functionality a little bit complex, is that it also has a really simple gradient to calculate, which looks like this. It looks a little bit like a Gaussian. And another thing is the sigmoid most of the times is also used in cases where you need to map your input into a specific region. So for instance, the ReLU, as you can see, has as an output dimension, it ranges between 0 and infinity, which is okay if your problem allows this, is okay for having in outputs between 0 and infinity. But think of it, for instance, here in the output layer. In some cases, for instance, let's say you want to estimate a probability for something. You better want your probability to be in the range of 0 and between 0 and 1, because you don't want to have negative probability, and you also don't want to have a probability which is bigger than 1. So you need some function which maps it onto the space. And in these cases, the sigmoid function is used, for instance, in the output layer to bring whatever's happening before into the right region, into the right range. Okay. As it's already written on the chat, and I just want to repeat it, if you have any questions in between, please feel free to interrupt me. And here you can just ask it and on Zoom, write it into the chat, for instance. Okay, there's obviously this, let's say, overview here of activation function is obviously not complete. First of all, just out of these four, you can construct any kind of linear combination out of these, which gives you some other activation function, which might be some balance between the profits and trade-offs of the various activation functions, or you can construct completely new ones if you wish. So there are way more out on the market, which you can just, for instance, if you go on Google and check activation functions, there will be plenty of them, and also certain scenarios where you want to use them or where you rather don't want to use them. But the rules of thumb, I would say, is if you have no idea, no, let's say, previous experience or knowledge, you should in most cases just start with a redo activation in the hidden layers, because in most cases you do not do anything wrong with that. And for the output layer, you have to consider what is your target space. And then if you get bad results, you can then still think about adjusting it slightly. So this is always a good starting point, going with the redo. Okay. The next thing we obviously need, okay, we have our input, which are the x's here, and we have our target, which is the f of x. And then obviously we need to train, which means we need to know, is the output value good in some way? And for this, we also need some truth of the target, which I denoted here with this y. And then we need some function which evaluates this. And in principle, you call it either as a training objective or loss function or objective function or cost function. So there are various names for the same thing. And it's essentially a measure of comparing the predicted output with the truth in order to get an estimate how good or how bad is your method performing. So for instance, because that's what we're going to do later in the example, for a classification task, a standard loss function people use is the binary cross entropy if you have just two different kind of classes. So if you have considered between 0 and 1. And it's essentially multiplying the label. So for instance, if you put in a cat image and you label cat as 1, you would say this is 1. And you weight this with the log of the probability of the prediction of your method. So if your method says, yeah, okay, this is also probability of 1, then you get log of 1, which is 0, which means this sums up to 0, which is what you want, because the main objective in the end is that your quality measure should be maximized or minimized. So that depends the sign here. So, okay, if the target value is 1, obviously you also want that this is 1 in order to get a minimum or a maximum, depending on what you find. And other way around, if your target value is, if your target value is 0, then you want it the other way around, so that things are vanishing. Okay. But you obviously here again, the construction of the loss function in most cases is rather straightforward. So whenever you have a classification, you either go with the binary cross entropy or with the categorical cross entropy. You can just look it up. And in regression, you can use something like a mean squared error, which is essentially just the differences between the prediction and the truth, and you sum over the squares of those differences to get an estimate, and this you want to minimize. But there are obviously cases when it's a let's say non-standard problem, where the loss function is not that straightforward, and you really have to take care that you construct it properly. So this is kind of also within the art of designing a neural network, defining a loss function, which on one hand properly describes the let's say the target you wanna achieve, but also is, and this is one thing we'll see later, is also numerically stable, because whatever you do here, you don't do minimization analytically, you do it numerically. And this is essentially linked to the training part. So how does a neural network learn? And the basic concept of this on how neural network learns is essentially backpropagation. And I think this was already mentioned like in the 1950s by Rosenblatt, and I think latest by Otja in the 80s or something. They already theoretically derived on how you would update the neural network weights, even though they did not have proper computers to do so. But the theory behind it was already there. Okay, so what's the idea? So the idea, as I said, you want to find a minimum or maximum. Usually you go for the minimum of this loss function. Okay, what do we know from analysis course? If you want to find the minimum of something, you take the derivative and find the zero. Find the zeros in order to find the extrema, right? And that's essentially what you also do. But how does it work if you do it numerically? Okay, first of all, you have to calculate all these gradients here. So if you have the loss function, you want to take the gradients with respect to all weights, and this number of weights can be huge. This can be, if you have like really small neural network, this can just be hundreds of network parameters. But if you have like really, really big neural networks, which are really capable of, for instance, generating real human faces, for instance, you can have millions of those. So you can imagine calculating a gradient of the scalar with respect to millions of weights gives you a rather huge expression, because you have to consider that you have a chain rule and you have to backpropagate, or you have to calculate the gradient of each layer with respect to the previous layer, and then you have to go back continuously until you end up at your input. So you get a huge stack of gradients here and derivatives. Okay. How this is done numerically, I will show you in the Python code. But let's assume you have calculated this gradient here. And okay, the question is now, how do I obtain a better next guess for the W's if I have calculated this? The most simple way of doing so is by so-called stochastic gradient descent. Okay, here I slightly changed notation, sorry for that. So now the W's are the thetas here. So let's assume at training period t, you have some parameters theta. And in order to get to the next, in our best case, better value, you calculate this gradient and subtract it from your previous weight value with some learning rate, which is this eta here. So what you do here is essentially a Taylor expansion, if you wish, of this loss function, where you think of you have added some small amount to it. And you only consider the first order, because otherwise you would need to calculate the gradient of a gradient, and then it gets like computationally really inefficient. So I mean, in principle, this would be a good thing, because then you would do a more precise update. But for now, we have computational limitations and we cannot do that. So we restrict ourselves to the basic idea of this. Okay, one important parameter here is obviously this theta, which is the learning rate. And this is in principle nothing else in the step size. Like you have some gradient of some loss function, like for instance this here, and you calculate the gradient here, and then you walk along the gradient, which would be something like this. And you walk along with some step size. Then you do this, and then you maybe jump to this position. Okay, and then you calculate the gradient again with your step size, and then you jump to here, and you do it again, and you jump there and there and there. Perfect, and in the best case, you end up in the minimum. However, it can also happen, for instance, if you're here and you have picked a too large step size, You go here in the next step, and then in the next step you end up here, and you actually walk out of the minima. Which means you have to be careful in which kind of, let's say, learning rate you choose. But the thing is, this is a hyperparameter of your network, which means it's not like, okay, I have problem X, I have no network Y, and then I know I have to pick the learning rate such as this. Because I mean, this here is a really simplified example of a loss, right? Because the loss is not depending on one parameter, it depends on millions. So you really cannot say usually in advance what the, let's say, the loss in the learning rate should look like. So there's certain techniques to make things better. I would just shortly want to mention two things. So first of all, something which is pretty smart usually to do is to start with a rather large learning rate, which is linked to this, because what you really observe is that you don't have one minimum or one extremum in your surface, you have multiple of them, but they have different actual minimas, which is meant here by a global minimum and a local. So what you're interested in later is not ending up in this local minimum, you really want to end up in this global one. That's why it might be beneficial in the beginning of the training to have a rather large learning rate. So you're really exploring all of the landscape of your surface. And you get some feelings of where the local minimas are, and you get a feeling where is the actual minima you want to go in. And then over training, you usually decrease your learning rate such that once you end up in close to your global minimum, you're actually descending and going down. Okay. This is kind of, let's say, not easy, but at least okay to understand for this really I1D example. But obviously, this is a nice image taken from this nice website, losslandscapes.com. And if you have some time, I can also recommend to go on the website because there is also nice description how do you get those images. And okay, this is a project, I think it's a free project, open source, where they try to do kind of dimensionality reduction and projections in order to kind of visualize those high dimensional loss landscapes. So here, as a starting point, as I said, they have like 1 billion dimensions. So they have a lot of dimensions in this loss landscape. And then they use a lot of techniques like dimensionality reduction techniques, where you essentially try to remove dimensions which are not important in the considered cases. And then you take 2D slices. And then you can, on these 2D slices, do some interpretations. So for instance, as you see here, this like looks a little bit like a moon or the Mars, I don't know, surface, I would say. You have those different areas. And the lower the better, because that's the minimum. And the high things means this corresponds to a large loss. And okay, there you have different minimas, and that's what I mean. I mean, if you, for instance, start over here in this specific region, so, and if you would choose a small learning rate, this would mean you would go to the minimum of this. But nobody guarantees you a priori that this minimum or this minima here is better suited than this one. So in the beginning, it's sometimes helpful if you actually jump over the big mountains here and first check out the different minima. This is another visualization, which is also taken from this website. And this also describes a nice feature, which you might also you can kind of encounter if you do this example later, is that it can happen. It's not just it can happen, it will definitely happen if you train the same neural network twice after reanalyzation, that they end up at the same value of the loss function, but it's quite unlikely that the weights you obtain are exactly the same as before, because you're on this high-dimensional surface. And this is kind of meant by this mode connectivity, which is described here in this kind of canyon stylish picture here, that in principle this minima over here and this minima over here, they perform equally good, but they describe different points in your parameter space. And in principle, you can just walk along this valley and you will always have the same loss function, and you can actually interpolate between the different parameters. And this is actually a nice feature, because this kind of guarantees you, if this is true, that if you slightly wiggle around with your parameters, your loss is stable, which is a good thing, because you kind of want that your neural network is not completely unstable, and it's not like, I don't know, let's say on a saddle point, and if you just wiggle around a little bit, you're completely off. So that's something what you actually want. Okay. Something linked to this, what I just said about the stability, is if you have is linked to the concept of overfitting. So for instance, over here in the specific case, you have blue dots and red dots, and you try to train a neural network, for instance, to draw a boundary between those two classes. And like always, in all data you construct, the data is imperfect, which means you will always have noise on it. Which means in this specific case, there will be blue points which are in the red area, and there will also be some red points in the blue area, and this is perfectly fine. So what you want is that your neural network tries to ignore those outliers and draws in this black line as a separation curve. What you don't want is that it draws in the green line, okay? Because this would be overfitting. There you really try to get every single point of your training data correctly. But this does not mean this is a correct fitting function, because your training data is always just some finite size of whatever underlying probability distribution you're thinking of. So for instance, if you think of these points here, they might be drawn from some experiment. I have no idea which one, but in principle, let's say these are 1,000 points and you're training that. Okay, if you would assume you go with the green line, and now you say, oh, I have way more data now, I generated 1 million other points, and you throw them in as well, most likely the noise you would get in your finite size data, training data, will go away, and your function, your green function, will be completely wrong to a statistically independent sample. And that's linked to overfitting, because what you can think intuitively of is that if you have too many parameters for your training data, your network is not understanding the functional connection between input and output. It's more like, let's say, a medic student who's just learning by heart which input is connected to which output. So it's just learning by heart the connections. It's not understanding the features. It's just learning, okay, if I have point that one, I need to give this as an output. But that's not what you want. It's about finding correct patterns. Okay. How can I try to regularize this? So there are different techniques. So one thing you could do, for instance, are these L1 and L2 regularizations. They're pretty straightforward. There you essentially add an additional term to your loss function, which is essentially just the sum of the absolute values of your weights, which is the L1 loss, or a sum of the squared weights, which is the L2 loss. And now if you think of it, your objective is to minimize the loss function. So what you really want is that the sum of your weights is in best case not too big. This kind of minimizes or restricts your weights not to get too big, because that's usually not what you want. You don't want, if you for instance have 5 weights, you usually have better performances if the weights are all more or less in the same order of magnitude. It's not like one is at the order of 1 and the other one is 1 million or so. This can be a good point, and it might give you a really nice result for your specific training data, but then it's quite likely if you slightly change and take an independent sample, you're completely off. Another method, and this is also easy to understand if you think about this idea of that the neural network is essentially remembering by heart which input belongs to which output, is to insert something which is called drop out. And in drop out, what you do is you essentially doing, but this only appears during training, you randomly set some input nodes to 0. And this happens randomly. So you really force the neural network to understand the patterns and not just associate single neurons to specific inputs, for instance. But these are regularization methods you can use, you don't have to. But what you should do, and I would say you should not trust any machine learning researcher who's not doing this, is you have to try to identify if your network is overfitting or not. And this is really, really easy. The most simple thing you can do is, if you have a training set, or let's say you have some data, you split it in half. They're both drawn, they're both from the same underlying theory, but now there you have an independent sample because both data points are not the same. On one, you train, and you update your network and you get some loss function. And the other one, you don't train on, you just use it in the end to compare and calculate the loss. And then you compare the losses and the occurrences. And then you better want that the loss of your test sample is of the same size as of your training sample, because then you can be sure it really has only learned patterns and not has, I don't know, learned the training sample by heart. This comes with only one downside. So for instance, if you have, in physics, we usually don't have problems because we have a lot of data, so we don't really care. So we just take more data and we're happy. But there can be cases where it's hard to get new data sets, to get more data, because, I don't know, you have to get people doing any kind of surveys or for whatever reasons. And then if you have you split your data set in half, by construction, limit your data size you can use for training. This can be bad sometimes. One way around it, and that's why I'm mentioning it, is so-called cross-validation. What you do here is essentially you do the same splitting, and then you train your neural network twice. Once you train it on the one half and use the other half as validation, and compare those two of if there's overfitting happening, and in the second training, you train on the other one and validate on the other. And then you can, in the end, average over both results to get a better statistical result, while still taking care of you're not overfitting.
You say average the weight?
Sorry?
When you say average the weight,
for instance, yeah.
That works.
You can either average the weights, or you just average the network outputs, for instance. You could also do that. Okay. Next thing I would like to go into is some code example where I really show you what's going on. Okay. So for those of you, for this first example, I'm really gonna go through everything with you. So there's nothing you have to do now. But for later, what I highly recommend you. So first of all, everything is online, or I'm not sharing anymore, right? So sorry for those on Zoom. So everything, go back to where I was starting from. So this is the website, everything you need to find. So this PDF is uploaded here of the talk. And everything else you can, for instance, find here on GitHub. I made a repository, so everything is there. And there are essentially later 3 ways for you to go through the code depending on what you prefer. So the most simple way, no, it's not the most simple one. One way to do it, if you have Python on your laptop or your computer and you have everything kind of installed already, because you need to install Tensorflow, You can just download it or pull, you can just clone this repo and yeah, take it as it is and modify the notebooks in whatever way you want. Most cases, I assume, especially those which never worked on that, you don't have some TensorFlow environment on the laptop. Then I would recommend to use this Google Colab environment, which is, you can essentially just press here, and then you get on a website where you can then pick the different Jupyter notebooks I prepared for today. And you can also do this later, so I will keep them online, obviously in the repo as well. The only thing here you need to have is a Google account. So then if you have a Google account, you can open it and you will be happy. So let's just open it. Okay, and then it looks like this. If for whatever reason you don't like Google Colab because you say, no, I hate Google, I don't want to use it, I also created a binder hub where you can also do everything. I also hopefully set up the environments 100% correctly. It looks like this, and then it will load everything, and there you can also modify things. So the nice thing about this binder thing is you can directly modify stuff there and save it. If you open things in Google Colab, you cannot copy, so if you do changes here, for instance, if you write something, you cannot save it because you took the Jupyter notebook from my GitHub repository, because I don't want that, I don't know, 15 people working on the same time on the same Jupyter notebook. So you have to save it or copy it to your Google Drive konto, and then you can modify it the way you want. I mean, you can still modify it, you can just not save it, but you can just take a copy and put it to your Google Drive account, and then you can modify it. Okay. That's also the way I'm going to present it to you with this Google Colab, so that, yeah, I'm expecting most of you to going to use this one, so I'm also going to use this so you get an idea how this works. Okay, so let me start with the basics of TensorFlow, because whenever you think of machine learning, obviously, as I said, you need some algorithm, you need some framework in order to perform all those tasks. And there have been a lot of, okay, first of all, it appeared for whatever reason that people would like to do machine learning, you're doing it in Python. We're also doing it in Python today. In principle, you don't have to. You can also do it in C++ if you want. For whatever reason, Python got a winner in being the language for machine learning. But in principle, there's not a restriction to do it in Python. There's also a lot of libraries in R, and TensorFlow, which we're going to use today, also works also in C++. Okay. And as I said, so the reason why I'm presenting TensorFlow today is pretty straightforward and the answer is pretty simple. It's just because that's the framework I learned the first, I would say. If you would have asked me like 4 years ago, because right now there are essentially two big frameworks on the market. And I mean, today we do TensorFlow, but if you want to do something else in the future, you're highly welcome to do so. So there's either TensorFlow on the market, which is one big one, and it's by Google. That's why it's also pre-installed on the Google Colab website, because it's from Google. And the second one is PyTorch, which is from Facebook, or I don't know, maybe it's called Meta now because they changed their name, but it's Google versus Facebook. So you can decide which company you like the most or dislike the most and pick one or the other. As I said, like 3 or 4 years ago, one framework had some advantages over the other, and the other one more advantages over the other one. So for instance, 3 years ago, most people doing actual machine learning research prefer to use PyTorch. over TensorFlow because it was more easy to adjust things, and TensorFlow was more robust, especially if you want to apply this kind of machine learning not just on your laptop, but also, for instance, on a smartphone or something like that. But all this kind of changed since, I don't know, 2 years ago or 1.5 years ago when the new TensorFlow 2 came out, and since then there's, let's say, feature-wise and capability-wise, not much of a difference anymore between PyTorch and TensorFlow, and then it's really more about what you like personally more. Okay. Today we do TensorFlow, if you like it or not. But one nice thing about TensorFlow is that in most cases, if you're already familiar with NumPy, then you also know how to do the same thing in TensorFlow. One thing you always have to do whenever you want to use TensorFlow, obviously, you have to import a model. So you just do this. Okay, now telling me it's not authored by Google, because obviously this was not written by Google, but that's okay. I promise you I didn't put in any viruses or something. Okay, and then, yeah, you have to import TensorFlow, and then you can do whatever you do with NumPy as well. And then you can just, yeah, define, for instance, here some array which goes from 0 to 1 in 11 steps, for instance, and get this nice TF tensor, which is essentially the base class you construct almost everything from TensorFlow. And it's even easier. So for instance, you can also import NumPy if you want. It's also something you can always do. And okay, you can also really easy switch between NumPy arrays and TensorFlow arrays. So in most cases, if you define some NumPy array, I don't know, like this, you can always, let's define it here. And so what you always can do in order to translate some value or list into a tensor is to use this TF constant function. You can use this with scalars. You can do this with some lists, or what you can also do, let's call this x1 NumPy. Just insert a NumPy array here. Okay. And this will work in all cases, which is quite practical. So whenever you have something written in NumPy, you usually and you have arrays in NumPy, most of the cases fine with just doing TF constant of this NumPy array, and then everything is set up in a way that TensorFlow can handle it. One thing which is also interesting is what you can see here is that by kind of default, TensorFlow usually uses floats, so 32-bit floats, so it's a single position if you want. You can also obviously do integers, but then you just have to insert in this TF constant integer values. It does the type inference automatically. It's straightforward. It's the same way as it works in Python or NumPy as well. It's nothing really different. Okay, and what you also always see here is the shape, the dimensionality of how things look. Sometimes it might be beneficial, for instance, in cases when you train later on, you usually train in batches. And in most cases, when you set up your neural network or you define your inputs, you don't want to specify your batch size beforehand. You rather want to do this like on the fly when you actually train on it. That's when, so what you can also do, that's where this TF Keras layers input comes into play. You can also specify a shape which is non-valued at creation level or initialization level, but this will be So once you insert something into this input, an actual value, it automatically learns or infers the correct value for this num type that displays. So that's quite neat, because when you want to just do the training again and you change your batch size of your training data, you don't want to reinitialize your neural network for this because that's really impractical. Okay, that's quite nice. And you can also make this that it changes from entry to entry. That's perfectly fine. And one nice thing about TensorFlow, when you install it on a machine where there's a GPU available, you can also run everything on a GPU. And this is actually one nice thing about Google Colab. You can run everything also on the GPU if you like. So it's not your GPU on the computer, it's some Google GPU. And you can do this later if you want. So there's always this possibility to go to this edit and the network settings. And you can choose here a hardware accelerator. And you can choose between a GPU and a TPU actually. So there was some nice session this morning about CUDA and GPUs from Olivier. And TensorFlow, so assuming CUDA is properly installed on your system or your cluster, TensorFlow automatically gets that. So you don't have to do anything. Of course, you can force always your code to not use a GPU if you don't want to, or you can insist of installing it without GPU assistance. A specific thing of TensorFlow is that it also works with TPUs. This is a specific kind of hardware I don't want to talk about today, but this is also pretty interesting and yeah, something really connected only to neural networks. Okay. One important thing is, okay, we had this big chain of differentiations. We need to also perform this with TensorFlow, okay? And there where comes, that's like where the main idea from TensorFlow is to create a framework which allows for automatic differentiation. And it's implemented. And that's something what you see here. One important thing is, if you see here I'm not writing TF constant, I'm writing TF variable. And this is a small but an important difference, but it also makes sense logically. So if I just do here whatever it is, so I'm defining a variable x with value 2, then whenever I have to calculate gradients in TensorFlow, this is actually new in TensorFlow 2. You define a gradient environment in which you follow your variables. So it knows that, okay, there might be something to calculate. And then you really just enter, okay, that's okay. This width environment you might be familiar with from Python. And then you really just calculate the gradient. And then you get out 4, which is exactly what you would expect, right? Because you know the gradient of x squared is 2 times x. So if you insert 2, it should get out 4. Let's check if it's really correct. So let's, for instance, if you have x to the power 3, okay, you know from if you have marked classes, if you differentiate this, you get 3 times x squared. So if you put in 2, you get 2 to the power 2 is 4 times 3 should get out 12, right? And you see that TensorFlow is doing this nicely and correctly, and it knows kind of all these differentiation techniques. And this also works for even more complicated functions like exponential, logarithm, stuff like that. Okay, there are 2 remarks. First of all, this only works if you insert floats. If you try to put in an integer here, it will tell you a warning that it doesn't allow you to do it with integers because that's just how it's written internally. Okay. And then there comes another issue from NumPy because you could not calculate this gradient here, then NumPy obviously cannot. So what's happening here in this print statement is it's just that this TensorFlow object is translated into a NumPy object by this .numpy. This is the back translation one. And this back translation just doesn't work because this gradient doesn't exist. So you always have to make sure that this is true here. Another thing which also doesn't work is if you put in constant here. Then you will also see, okay, there's a problem because obviously if this is a constant, it cannot take a derivative, okay, because it's a constant. Which also makes sense. If you also say in math, this is a constant, then taking a derivative of it also doesn't make sense. It's just something you have to take care of. Okay, this is, let's say, basic TensorFlow. All right, so let me go back. The nice thing about TensorFlow is that it does not only come with the standard TensorFlow library, but it also has some really, really nice high-level interfaces, which kind of helps you with most of the things. So in most cases, you don't need to write everything with TensorFlow yourself. In some cases, you have to because you're having some really complicated example, but in most cases, you don't have to. Okay, so let's go through this. So the one big thing which is now implemented as a core, let's say, module of TensorFlow is Keras. Keras is quite known already years ago. Earlier it was a standalone thing, which themselves implemented TensorFlow as a backend. But I think also since TensorFlow 2, it's a core element of TensorFlow and they kind of merge together. Okay, now I want to talk about one problem, and I would say we do this problem, or let's say this, go through everything, and after this, this might be the best place then for a break. All right. Okay, let me first show you what this problem is about before we load the data set. Okay, open it here. This is some data set I just downloaded on, sorry? Oh. I can always look here. Thanks. This is just a data set which I just downloaded from the internet. Because whenever you can essentially just go to Google, enter, I don't know, machine learning data set, and then some keyword for what? Classification, image, regression, and then you find a lot of things. Okay, this is some business problem of a bank where a bank has a lot of customers. I think it's 10,000 or so, which is not a lot, but this is just a data set. And you have a lot of features which define what this customer is. So you have you have a name, you have the credit score, where those people come from. In this specific case, they are from France, Spain, and Germany. Unfortunately, I forgot to put in Belgium. Then you have obviously male and female people. They have a different age, different number of money on their account, number of products, and a lot of other things which are linked to their whatever bank is. And let's say the value of interest for the bank is the last thing, which means exited. This is now a list of customers which either still in the bank and are still customers, and some which left. Okay, those which are still in the bank, they are denoted with 0, and the ones with a 1 are those which left the bank. And the task here would be, let's assume you work with it for a bank, is okay, here is our data set from the last 2 years. Can you please predict, I don't know, which of our customers will likely to leave our bank? And then we might contact them and ask if they're happy with our bank, stuff like that. So you kind of support your customer service with this. So that's the idea. All right, so let's go back. I have to put on the share again. Okay. First thing we have to do is to insert or import TensorFlow again. Then we need NumPy because NumPy is in most cases needed. And we also import pandas. Pandas is a really, really powerful module, which is also always used, with which you can load almost all data sets you need. It's like the module for data scientists, I would say. Sometimes also really useful, especially if you have problems with your system, to check which TensorFlow version you have. Here now TensorFlow version 2.6 is pre-installed. It's just what you can check. Okay, and then we load in the data. And this should also work from your computer because I uploaded this data file also on the GitHub. One thing you see here, now we defined as the input values, all values starting from 3, except the last one. The reason for this is, if I open this again, maybe that's just the desktop, then it's easier. Okay. The reason for this is that the row number, the customer ID, and the name, these are no features which are by any means like relevant in order to predict something. That's why we leave them out, okay? And we only go to the second to last one because the exited is our target, and only all the other ones before are our features as an input. Okay, that's what you do with this ilog, and then you take the values of it. And then you can have a look at the features. So we have this credit score, the country where they're from, their gender, etc. And this is, okay, if they stayed in the bank or if they exited. Okay. One reason why I picked this example is because it already requires us to do some pre-processing, because most of the case you have to do this, and now you understand why you have to do it and how. So for instance, your neural network in the end is, as I said, weights times your inputs. And we have seen in this TensorFlow example, it expects naturally floating point numbers. Okay. You don't have to worry about those ones here. They will be translated from integer into floats. But there are other things like, for instance, female, which is a string, and France, which is a string, which you need to translate into something where the neural network can make sense of. Okay. One thing you can do, for instance, is called you just encode it in a different way. Okay, there is also you can for instance write something yourself, or you download something from scikit-learn, which offers a huge toolbox of pre-processing tools to exactly do this kind of thing. One thing we use here is so-called label encoder. And what it does, it checks row 2, which is this gender row, checks for the different numbers in the specific case of strings which appear. We only have male and female, and then associates a number to it. Okay, and the most straightforward thing to do is to, for instance, define female as 1 and male as 0, or the other way around. So you define it as a binary value. After this encoding, you see, okay, now you don't have female, male anymore, you have 0, 0, 0, 1s, etc. And in this specific case, female is now 0 and male is 1. Okay. The next thing here is we have those countries. Here it's a little bit more complicated because we don't only have 2 different kind of countries, but we have 3 of them. So we need some kind of one-hot encoding. That's the way you'd call it. And the idea is essentially, if you have, let's say, 5 classes, you translate those 1 row into 5 rows, where each row belongs to a different country, so each row belongs to a different class, and there's a 1 as an entry for into a row if it belongs to this class, and zeros in the other cases. Okay, and there's also something predefined which comes also with the scikit-learn, which is one hot encoder. That's the way that's the terminology you use for it. And this translates it. And what you get here is now here the first three not rows, sorry, columns belong now to the countries. So you see France is the first one, Spain seems to be the last one, and Germany must be in the middle one in this case. And that's the way how you decode your string values. One thing I also put in here is the shape. I forgot it earlier, but I should have put it in, is obviously now you enlarge your data set, right? Because you had one column of strings, and with this one hot encoding, you made more columns out of it because you did this encoding. So you need to then remember this, that you have now, let's say, 12 features actually, and not just 10, which was before. Okay, the next thing we do is, as already said in the PowerPoint slide, is that whenever you train a neural network, you better take care that you're not overfitting anything. So we have our data set, and in order to not overfit, and again, like always, you can always do everything by hand with standard tensor slicing, like it also works in NumPy. But you can also use this nice function, which is called train test split, where you essentially split your data sets. So this is the input, and this is your predicted target, into two kind of samples. You have the input train and the target train, and you have some test features and some test target. And those are, let's say, split from the original one. Let's just press the button. Okay. And here, as you can see, the test size is 0.2, which means that out of these 10,000 examples, I think we could actually check that. It was written in this shape here. Yeah, 10,000. This means 20% is now test size, which are means that 2,000 examples are test size. I just see there's one guy asking how to run it on Google Colab. I'm not sure if this is still unclear, but yeah, you just open it and then you can just press those buttons like I'm doing it now. Okay. Another thing which you also see in this features here is you have now 12 different features, and they all vary a lot in their input values. So for instance, for the estimated salaries, you have numbers which can go as high as 7,600 something. The credit score is around order of hundreds, and then have the age is out the order of 10. So there are in really different orders of magnitudes. And this can be problematic for a neural network, because what you really want is that a neural network, let's say in the beginning, is not biased by, for instance, the estimated salary just because it's a bigger number, right? You don't want that it thinks this is more important than the other features. So one thing you do is the so-called pre-processing standard scaler. And what this does is pretty simple. It goes into each column individually, calculates the mean and the variance, and then redefines it such that the rescaled values have a mean of 0 and a variance of 1. And then all the features are in the same range, and they're not, I don't know, and you don't have a bias automatically. Okay, that's what we did now. Okay, next thing is what we do is we train a neural network. And there are different levels of functions of interfaces you can use within TensorFlow and with Keras. The most straightforward one is the sequential mode, which are linked here. And the only thing you have to specify here is essentially the number of units and activation function. And you define it with TF-Kira sequential. And then you essentially just stack those layers. And this dense layer is this standard feed-forward neural network I also showed you in this introductory slides. You can either list all layers you want within these brackets and separate them by this comma, or you can also, if you later realize you forgot something, you can also just append something or add with this add function here. So these two are now our hidden layers. So we have 2 hidden layers with 6 units and an activation function of ReLU. And in the output, because we want to have one output, which is did he exit or not? It's 1 dimension. That's why we take 1 unit. And we want to have a probability, if you wish. So 0 should belong to did not exit. Exactly 1, it means it exited. So we apply an activation function with sigma. Okay. One thing you note here is that the number of units is smaller. So the number of units in hidden layers is smaller than the number of nodes you have in the input layer. This is not always the case, but it can be useful. For instance, if you assume that not all features are relevant, or there might be a way to compress the information, which might be spread over more features, so that the actual decrease of freedom is actually less than what the way the input parameters, the input space is parameterized. Okay, there's also a second way to parameterize things, but I just shortly go over it. It's functional API. It's actually the same thing. This line of code here is the same as these two combined. The only difference is that you have to actually specify what the input shape looks like. This might be sometimes helpful, so you're really aware of what you're doing and you're not running into some problems. And another thing about the functional API, which I sometimes, or most of the cases when the networks become complicated is that you can print out a summary. So what is the input, what is the output, and how many nodes and units do you have, and how many parameters, so actual training rates do you have. This feature of the summary you cannot do with the sequential one. So whenever it's getting more complicated, I would always recommend going with the functional API. It's still really, really simple, but you have this nice feature that you can print out a summary and it gets an idea of what's going on. Okay, and then after this is done, we need to compile the network. This is something, it's a Keras function where you tell the network now 3 things. First of all, you tell them which optimizer to use. So as I said, standard way of doing this backpropagation and learning the new weights is the stochastic gradient descent. This is in most cases not the most optimal one. There are variations of the stochastic gradient descent on the market. The most used is this add-on. I'm not going into details about that. You can look it up. It's adding things like momentum and stuff like that. It's like having the idea if you have, for instance, some rolling ball where you're just on a saddle point and the gradient would be 0. You don't want that the ball stops there. And if you think physically, if you add something like momentum, it keeps on rolling over the saddle point and maybe continuous rolling. This is like the same idea you can also implement. Okay, so this is the optimizer, and also for the later example, I recommend to use add-on. Then we define loss, and as we have a classification, we use the binary cross entropy, and then we also add a metric, which essentially tells you on the fly how many predictions were correct compared to the truth. So if it predicts 0, for instance, but it's actually 1, then the accuracy, so in this specific case, would be 0. And this tells you out of how many, so this gives you a percentage level. And this is quite neat because in most cases, just the value of the loss function is sometimes really hard to digest and understand what it actually means. So it really sometimes helpful to add another kind of metric in order to quantify the quality. Okay, so let's do that. I compile it. All right, and then I train it. I put in my input features, my target. I define a batch size. Usually it's something like 32, but depends on the problem. And I run for 100 epochs. Okay, I can just press enter. Now this goes really fast. Even though I'm not running on the GPU, I could do, then it should be even faster, but I'm not doing it now because this is already quite fast here.
Another question?
Sorry, sure.
The training rate is incorporating Adam?
Yeah, I didn't mention it. So if you don't separately mention it, it's a standard Adam learning rate, which is probably 10 to the minus 2 or something.
Same question in terms of accuracy. Can you use that as a for loss?
I think you can force to do this, but I'm not sure if it works actually. Because accuracy relies, so what accuracy internally does is it really compares the integer value classes. So if your output of your neural network is, for instance, probability of 0.3, this will be translated into class 0, and then this will be compared. And this might be problematic because you rather want to have smooth values and not dope, because you need to calculate gradients from. Okay, so here you can always just Google, so just enter Adam, and there it's seen. Okay, so the standard learning rate here is 10 to the minus 3. Okay, now it's run. So now you see the final loss was 0.33. Okay, whatever this means, that's what the loss is. And the accuracy was 86%. Okay, that's not perfect, but it's also not bad. I mean, you can obviously twiggle around, and you could also play around with adding more units, more layers, and you will probably get better or worse accuracy, but this is really then about choose the correct hyperparameters. But that's not the point about the session. Okay, but now you get some this. One nice thing we could do is now, for instance, before we get to the signal prediction, is now evaluating the test set results. Okay, so what I'm doing now, the network is trained. I'm using this predict function to predict the output of the test sample. This I can do here. And then here I'm calculating when y predict is bigger than 0.5. So here I'm doing actually this translation to 0.1. And then here I'm just printing the output of the neural network and the truth. And here you can see, okay, here there's a mismatch. And in the other cases, which at least those which are shown, it seems to be correct. There's also a way of doing this a little bit more properly, which is linked to two things. So first of all, you can now calculate this accuracy score also for the test set. And the next thing is a confusion matrix. Let me first talk about the accuracy. So this accuracy is the same thing as it is being calculated during the training, but now obviously not on the training data set, but on the test set. And as you can see here, this test accuracy is 86.2%, and here we have 86.5%. So it's slightly worse, which is okay, but more or less exactly the same, which means we're definitely sure we didn't have any overfitting. This is good. All right. The next thing is this confusion matrix. So this is pretty similar, pretty easy. So on the left-hand side, we have the predicted classes, and on the right-hand side, the truth classes. And then you have a matrix, right? You have predicted class 1 and correct class 1. So the diagonal entries means those are the correct ones. And the off diagonals means there you have mismatched. So you either have predicted exited, but it's actually did not exit, or the other way. And this is also quite useful sometimes to cross-check your results. All right. I would suggest making a break here of 10 minutes, unless there are questions.
Yeah, okay. I mean, all of the overfitting methods.
Sorry?
In this case, you didn't pass the training method, the test sample.
Yes.
With your, say, all the stuff, the optimize this case. So all the things you know, how Adam is preventing the.
Well, I mean, here I'm not training on a test sample.
Yeah, no, exactly. So in principle, you can overfit on the sample. And then you can test sample.
Yes.
So
Yes.
that is possible.
Yes. I mean, might be even already possible if I change something to the network. I can in the break try to run a network which is overfitting classically. So this can happen. I mean, obviously, I rather pick the small network here, but if I go way, way bigger, then it's quite likely that I'm overfitting. Before we start with the next part, and those which are already back, so I shortly broke my neural network. I essentially just added another layer and increased the number of units to 32. The training got better in the sense that the loss was smaller on the training set, and also accuracy went up to 90%. But the test set accuracy is just 84%. There you really can see, okay, they have overfitting. I mean, it's not a big margin, but still you see it's better. And there you would say, okay, yeah, my network is too powerful. I need to make it a little bit less strong, or find a way that it's not overfitting, even though it's powerful. With this regularization methods I mentioned, like adding in some dropouts. You are fine. Let's continue. Let's say a second part where you are also have to do some stuff. Now I want to shortly give you some intuition about convolution. Yeah, I just saw it. Yes, so this parameter I'm not sure which parameter optimization you mean. If you mean the training ways, then yes, Adam does that. It uses the stochastic gradient descent. And yeah, I'm not sure if this answers the question. Otherwise, you can write in the chat again, and I try to answer it again later. Okay, so short intuition about convolutional neural networks. So here I have a nice image which you can look at. And this is quite interesting because if you, for instance, focus while looking a little bit on the right-hand side, and you just see the face a little bit to the left, what you see or your brain and the brain impression is that the man looks to the right. While if you look on the left-hand side, your impression is that it looks at you. So you definitely see your network tries to, your brain recognizes some patterns in parts of the image, which then translate into, okay, it's a man looking to the right, or it's a man looking at you. And this is quite interesting because obviously there's just a pattern, which is on the right-hand side visible, which gives you the one hint, and then there's a different pattern on the left-hand side, and the brain has kind of problems in how to sort that out while looking on that. And there's another example which you might know, which is that one where it's either an old lady or a young lady. So the old lady had like the scarf here with the hair. This is the eye. This is the other eye, and this is the big nose. And this is the mouth and the chin. While the young lady is the eye here with the nose, and this is the chin, and this is just the, yes, I don't know. And this is the ear, so it's looking to the left. And also there, it's a little bit confusing for the brain how to actually say what's going on here. And what you see is that even we if we look at images, we not evaluate the total image at the entire image at once. We kind of separate it into patches, and depending on which patch our focus is on, we identify things differently, right? So even on this image, as a human, you would say, hey, it's a young lady, but it can also be an old lady. And in a similar way, also neural networks work. And that's also the idea of convolutional networks, that most of the things we see in images work patches-wise and how different pixels are related to each other. So you see structures like edges and stuff like that. And that's the idea of a convolutional neural network. And what does it do in principle? A convolutional network, instead of just taking a plain vector of numbers, it takes an actual image as an input, does some kind of transformations with it, and in the end, in most cases, it's just a classifier. You classify the class. This can be either just two classes, or in principle, you're not limited to two classes. You could also do several of them. Okay. How does it do it? So the first step within this transformation, which I'm going to explain, is the convolution. The second step is a pooling. And last but not least, you have some kind of full connection layers, which is essentially the same kind of layers we just had learned about, which is in the end before you pipe everything into the last layer where you do this binary step. Okay. And if you wish, the core of the convolutional neural networks are the first two steps. And the last step really only is a way after doing this convolutional steps to translate it again back into this vectorial one-dimensional form where you can have class 1 or class 2. So this is really just bringing it back into a form where you can train a lot on. Okay, what is a convolution? I mean, mathematically, it's pretty much that, but that's obviously not how a neural network works. Convolution is pretty similar, and it works in a similar way, but of course discrete in the specific case. Let's imagine you have this image here, and you apply on that a filter, which is essentially something like a scan over your image, which tries to find specific kind of features, and which kind of features are defined in this filter, and it tries to find these kind of features within this image. And then it does a convolution. And the way it does it is essentially described here. You take 9 times 0 plus 2 times 4, and you just go line by line, and then you add everything up, and this gives you one value, which is 16. And this is the convoluted information. All right. And then you essentially, this gives you this value, and then you scan over it. So the next step, this filter will be shifted one step to the right, and you evaluate this patch. And then you get the next number. And by this, you compare this filter, which is kind of a feature you assume, over the various patches or the parts of the image. Okay. One thing you really notice if you do it like this, in the specific case, you also downscale your image. So here you have a 1, 2, 3, 4, 5 times 5 pixel image. And if you go with the filter over it like this, you end up with a 3 times 3 image. So you get a smaller image. This is okay, because in the end of the day, what you always want is kind of dimensional reproduction, because even, I mean, if you have a big image of 512 times 512 pixels, for instance, not in every image, and not in every pixel, there's information you need. So you obviously always want to go down in dimensions. This can either be done in this way, by going through the image like this. However, actually, in most cases, you do something like padding, which is some step in the convolution where you add zeros at the outside of this image and in a specific amount. So you either don't add any padding, this is exactly this image, or you add so many zeros on the outside that when you go over this image with the filter, you end up at the same size in the output. So you would, in this specific case, since this is 3 times 3, you would obviously require to have zeros just once out the side also, around the thing. So zeros everywhere, like a big boundary. Okay. And then you would have a new, and then obviously you don't just apply one filter, you apply several of them, because each filter essentially tests a different kind of feature your network expects. And then, let's say you apply 32 filters, you essentially generate out of one image 32 new feature maps, you call them. And the filters you apply, they are now playing the role of the weights as in the normal part. So the entries of the filter, or how the filters look like, this is not fixed. This is the thing which can be trained. Okay, so this is like the network tries to adjust the filter in such a way that it extracts more features the best. So the more features it can extract, the better it is. All right, so you translate one image into, let's say, 32 filters, so you get 32 feature maps. Okay. Another method in downscaling things and really only extracting the necessary information, which is also used quite often, is pooling. And there are two kinds of poolings which are used. There's either the max pooling, so you, for instance, have this 2.2 pooling, where you just look into all those patches, how's it look, and then max pooling, as the name suggests, just take out the maximum value. Okay, this can be beneficial depending on what kind of feature you look at, for instance. And you also can do average pooling. From a numerical and, let's say, computational point of view, max pooling is more efficient, right? Because you just throw away most of the points, you just keep one, while average pooling, you have to sum them and take the average. So this is a little bit more expensive, but it also seems that average pooling is also a little bit better because you don't throw things away. But it turns out, actually, in practice, max pooling performs equally good. So most people then just use max pooling because it's just a little bit faster. All right. And if you want to think of this convolution and pooling, it's essentially like this hierarchy thing you see here. You start with, let's say, an image of a bicycle, and then depending on the level of your, let's say, convolution and then down pooling things of these different feature maps, you essentially separate this bicycle into its separate parts and features. So, okay, I have this image, then there might be one filter which always checks for the wheels, and there's one filter which checks for pedals and stuff like that, and then you kind of disassemble effectively your product. And now these features here can now be encoded. So then now you have a number of feature maps, and those you then just encode back into floating numbers, which is done mathematically by a step which is called flatten. So you really just make your image-like structure back into a number row. And from this, it's just an encoding, right? And from this, you then try to learn with an additional fully connected part what class it is. This is how the full picture looks like. So you have an input image, then you do some convolution, and then you do some padding. Here, this is when it's called valid padding. This always means that no padding is done. It's a little bit confusing sometimes. That's why this input image is 28 times 28, and those feature maps is 24 times 24. And you don't have one image anymore, you have N1 images because you applied N1 filters. All right, then you do max pooling, and then you go on like this. And then you go down, and in the end you flatten everything, and then you have again some fully connected, and then you end up with the output layer. And then here you usually have, for each class, you have a node. So if you have 10 classes, like for instance, you want to categorize numbers from 0 to 10, you have 10 nodes. And that's the most straightforward way to do it. Obviously, if you only have two classes, you have two options. You can either take two nodes and take the categorical cross entropy, or you just take one node, because if it's only two classes, I mean, you can also encode this in one node only, where one class is 0 and the other class is 1. So there, both is perfectly fine. It's just in the end, like the combination of the nodes and then the combination of the loss functions should end up at the same thing. All right. This is the ingredients you need to have. Now I prepared also for this a nice code example for you, which is also in the Colab, and everything is there. And so what I did is I prepared 10,000, a data set. Just look into it. Okay, so just load everything. So I helped you a little bit because you do need to do some pre-processing. It might be a little bit too complicated to find this out yourself. Okay, then you can download it here. It should download automatically a zip, unzip it, and put it into a folder so that it can be found. It's actually quite fast, so these Google servers are not too bad. All right, then you have a folder after doing this step where you have a data set. This folder is called data set. Within you have a signal prediction. That's something we use for later. Then we have a test set. And in each there's this folder cats and dogs. And in the training set also cats and dogs. And in this folder cats, there are a bunch of images of cats and dogs. Okay, so for instance, I can download this one here. You have something like this. Nice little kitty. Okay, perfect. And there are a lot of them. All right, so the next step here, this is kind of Kera's internal function, which helps you a little bit. This is this image data generator. This is quite nice because this generates you a proper training set out of a folder structure. That's why these folders are structured in this way, where you have within this training set a folder which is called cats and another folder which is called dogs. So Keras automatically recognizes the number of folders, then it knows how many classes there are, and correctly, and now it gives them the constructs the features out of that and also gives them class labels automatically. Just have to tell them here where to look at. And then class mode, you can also define. Obviously, binary only works if you only have two classes. But in principle, here you can also pick categorical, but then you have to keep this in mind when you construct your neural network. Okay. One other thing which is happening is this rescale. Because whenever you have an image, you usually have a scale between 0 and 255, which is the value of this pixel. Okay. And this we scale down so that we are in the range of 0 and 1, so that we are in a specific range. Another thing which I didn't mention is that for color images, you're actually not considering it as one image, you're considering it as 3 images for red, green, blue. So these RGB values for each color, you have a different image in this specific case. That's why your input has 3 channels already in the beginning. You have different color channels because you have seen the images with colors. All right, here I'm preparing a training data set. And here I'm also preparing the, here I'm preparing the training data set. here in this image data, the image data generator, they are preprocessed, they are rescaled. And one nice thing, which is also nice to have here, is it also transforms them randomly. Why is this important? For instance, when you have a cat image, you don't want that your neural network thinks it's a completely different object just because it's rotated a little bit or because it's flipped. So you want to make it robust against these kind of translations. And what this image data generator does in a really simple way, it takes, let's say, your 10,000 images, and on all of them, it randomly applies additional rotations, flippings, etc. So you effectively have more images to play with, so that it doesn't care about the angle of your cat face smiling. Okay, and then here it does it pipes it in such a way that it knows which class it is, and it also prefetches it into batch sizes. And it also classifies it as 64 times 64 images. Okay. Okay, there are 8,000 images in it. Then you can do the same thing with the test set. Here you should note, I'm almost doing the same thing, but here with the test set, I only do this rescale because for the test set, I'm not training on, I'm just evaluating. So I don't care for evaluation that I have to flip or kind of enlarge the data set. So I'm just doing the rescaling. All right. And then part 2 and 3 and 4 would be your part. And I've kind of give you some help with this needed parts and also with links in it and where to find things. You should build a convolutional neural network, which now consists of a combination of convolutional layers, pooling layer. You can define as many as you want. One thing I can already warn you, the convolutional layers are quite costly. So I would not go with more than 3 of them, because otherwise it might take quite long to run it, even if you turn on the GPU. Yes, if you want and you feel like really confident, you can also check out dropout, but you don't have to. So just feel free to play around with it. Yeah, this is like building the CNN. You can also choose whatever you like, the functional IP or sequential. It doesn't really matter. Whatever you think suits better. For both I've added the links, so if you want to look up again how that worked. Or if you're here, you can also ask me. The others in the chat might be a little bit more difficult to ask me here, but yeah. So this is essentially building a CNN. You can also, of course, open, for instance, the other file we did earlier to check like what the construction looks like, right? Then obviously you remember you need to do the compile it. There you can more or less copy it from the old one, but I just left it out here so that you at least remember what to do. And in the end, you do this fitting where you actually train it. All right. And once you did this, okay, yeah, one thing I forgot to write in here in this training. One thing you can do in this training fit function, let me open it. You can already provide the fit function with the test data set, which means it already, while training, also evaluates it on test data set. So you don't have to do this step of evaluating afterwards separately. You can do it on the fly. Why I'm saying that is you should use this for model fit function as we did it before, but also directly provide it with this validation. So it's called validation set in the fit function, but we just provide it with this test set we defined here. So you automatically also see, is your network overfitting or not? So you also get an estimate of this. Yeah, all right. And in the end, you can then directly check on those 2 pictures, which are in a single prediction. I mean, you can have a look at it yourself. before, or you don't have a look at it before. There are two images, so it's cat or dog 1, cat or dog 2. And then you can ask your network what it is and to check if it's correct predicting the right class. I think as we have only 10 minutes left, I would suggest that I shortly show what I did. And I will upload also my solutions, and all material is still online. So yeah, it's as I said, it's why I started mine already quite early, because I knew it's going to train a while. Okay. So here I have opened my solution, which I will upload. Which you should see now. Okay, so one thing, so this training set, which is created here, actually consists of, it's essentially a tuple which consists of both the X values and the Y values. So you can just print them batch-wise. So the one entry is the label, and the 0 entry is the image. That's why you get those big arrays here. Okay, and then I created a rather simple neural network here. I've added convolution with 32 filters, kernel size of 3, activation of redo. Then you have to have in the first convolution, you have to specify the input shape. Then I did a pooling. So I pulled down pool size of 2 and the stride of 2. So I'm really just taking, essentially going down from 64 to 32, this step here. And yeah, here, just yeah, and then I did a flatten. Then I added another connector in between, which goes down to 128. Because I thought, okay, might be otherwise a little bit thick. Or too easy. So here you can also print it, how it looks like. I realized it actually works. Maybe I did something wrong when I tested it. Or it's now implemented, I don't know. So here you can really see I have 800,000 parameters already, which most of them come from the dense layer in my case. So I could also leave that out. Here you get some idea of the structure, what's going on. 32 channels, and then how it's like scaled down. Okay, then I compiled it with Adam using the binary cross entropy. I used the matrix of accuracy. And then I trained. So I implemented X as training set, and it automatically detects how to handle this. I also added already on top directly the validation set, and I run it for 25 epochs. I also turned on the GPU acceleration, and even with that, every epoch took 40 seconds, which is actually not too bad. So it ran 15 minutes. And after 50 minutes, I got an accuracy of 85%. But what you can already see here in my example is that the test accuracy is only 80%. So I'm definitely overfitting here, which you can now twiggle around a little bit by making the network smaller. For instance, I could remove this additional dense layer with 128 units, which made those 800,000 parameters. That's probably just too much. Or I could add some dropout anywhere. So that's definitely something to fine tune. So I will upload the solution. So if you want, you can even play around with the solution and just later, and I don't know, make it, yeah, less overfitting, for instance, or improve it or for whatever reason. All right, then I loaded the images, and I'm not sure if you already looked into it. So let's go for cat and dog 1, and then I wrote, so that's here, I'm reprocessing the image because I'm first loading it. Then in order to pipe it into my network, I also have to rescale it because my network is expecting it that it's rescaled. And the image itself, if I don't do anything to it, has the dimension 64 times 64. And so you have to expand, and okay, and it's expecting, no, it has the dimension 64.643. But if you put it into predict, the network itself also expects a dimension for the batch size. That's just the way it's constructed. That's why I'm kind of artificially just creating an additional dimension for the batch size, which is just 1 in this specific case. Then I can do this predict here. Okay, then as I said, cat should belong to class 0 and dog to class 1. That's why I said, okay, if this result is bigger than 0.5, then it should be dog, otherwise it's cat. Okay, so let's check. It's picture 1, and this is a dog. The network says, now we can have a look. Okay, looks like a dog, I would say. So there the network is correct, and then we can check the other image. And there it tells me, okay, it's a cat. And then we can check. That's a big image, but it looks like a cat. And this is quite nice. One thing I also checked while I was preparing this is that this is really important that you keep in mind that you did some pre-processing to your data. Because if you don't do this or to the test image, you can get quite different results. For instance, let's do it to the first image. Just leave out this 255. Okay, it's still telling me it's a dog. So I could think, oh, it still works. But I'm pretty sure if I put in here now the second one where it told me it is a cat, it's still telling me now it's a dog. Even though it's actually a cat and the network was able to correctly predict it as a cat, because now every entry is really, really big and the network might have learned that big entries, whatever reason, now belongs to the class of the dog, or for whatever reason. Or you can even directly print what the result looks like. These are the things that always happen if you're writing it in front of people. So yeah, it just gives you the value of more or less exactly 1, which is usually really unlikely, which means that it might be that for every big value, it just gives you 1s.
Yeah, you have a sequence, right?
Yes.
That's so important.
Exactly, that's the thing. You have a signal in the end, and if there are large values coming in, and it's not trained to do so, then the weights are, so the weights also have an order of magnitude, which are expecting that the values which come in are between range of 0 and 1. And they're adjusted to this value range. And now there comes something in which is 250. Then everything gets multiplied, and in the end, you more or less end up that everything is done. So this is an example where you see, okay, it's really important to keep in mind you did some pre-processing, and you have to keep in mind you also have to do the same pre-processing to your test data before applying it. Otherwise, you get completely wrong results. Yes. Brings me to the end. There's only one thing left I wanted to shortly mention, which is for those which are interested in where machine learning is actually used in physics or particle physics, because that's what I'm working on. There is this really, really nice, well-maintained website on GitHub, which is this HepML Living Review, where the authors of this website are currently checking archive for really all HEP, Pheno, and HEPX papers, which are somehow using machine learning methods. And yeah, that's really interesting. If you're like, even if you're not a physicist and you're participating today, I don't know, you can still see where it's actually applied to actual physics or actual science examples and not just about distinguishing cats and dogs. Yeah, because these CNNs are actually also used for physicists available present for instance, tagging, top tagging, for example, where you have chat images and you take this as images to train on. It's quite interesting.